All right, 2.8 absolute value functions. We're just going to take everything that we talked about in class during the exploration, and we're going to kind of summarize it all in our notes and then apply it to a couple of absolute value functions. So let's talk about the graph of y equals the absolute value of x, or f of x equals the absolute value of x. Okay, so as you saw today, this is like a V. And we could get that by doing an input-output table, but your goal is, as we move forward, not to make an input-output table for every single graph, because eventually you're not going to know what the graph looks like, and it's just going to be a mess. So the goal is that we get to a point where we know, hey, I know what an absolute value graph looks like. So if you remember, when we plugged in 1, we got 1 out. When we plugged in 2, we got 2 out, and so on. So basically, the right-hand side of this looked like basically a line with a slope of 1. And it was symmetric in this y-axis. So in other words, it was reflected over the y-axis. If I plugged in 0, I got 0. And the same if you plugged in negative 1, you got positive 1, right? The absolute value of negative 1 is positive 1. Plug in negative 2, I get positive 2, and so on. So that's basically a graph. It looks like a V. The left-hand side looks like a line with a negative 1 slope. And the right-hand side looks like a line with a positive 1 slope. Okay, so for an absolute value function, this is right here. This is our parent graph. And then we do a whole bunch of stuff to it with transformations. Okay, so let's do absolute value. So the generic form of an absolute value function with all of the transformations being done to it looks like this. Okay, so notice you have an A, an H, and a K. So that's what we've added to this parent function. Now we're going to talk about what each one of these things do. So first of all, your H is your horizontal shift, or your horizontal translation. Your K is your vertical translation. And your A is your vertical dilation. These should seem very familiar to you from geometry. So if I horizontally shift my parent graph, who currently has a vertex, your vertex being like your highest or lowest point. Okay, my vertex currently is at 0, 0. If I shift it horizontally, H units, and vertically K units, then at any point I know my vertex based on what H and K are. Okay, so I'm going to put some bullets here. So the first thing is your vertex. Your vertex is always going to be at HK. Now again, your vertex, this is your highest or lowest point. And it'll vary depending on which way this thing's opening. So right now this is opening up, so my vertex is my lowest point. The absolute value function will always be symmetric. Think of like a line of reflection. In the line, x equals h. Okay, let's see. I'm going to use a highlighter for this. So the line x equals h, that's how much horizontal translation we've done. Well, right now we haven't done it at all. So right now, my line of symmetry goes right along with the y-axis. Okay, so right now my line of symmetry is x equals 0. So if this had been shifted over 2 units, then my line of symmetry would be at x equals 2. Okay, A is your vertical dilation. Okay, so if we have, let's see, the absolute value of A, so always think about it as positive. The absolute value of A being greater than 1, then we have a vertical stretch, meaning it gets thinner and taller. However, if that absolute value of A is in between 0 and 1, then we have a vertical shrink, or in other words, it gets shorter. Right now, we won't talk about horizontal stretch or horizontal shrink. I'll save that for pre-calculus. Also, A has some other stuff that it does. So if A is a positive number, meaning it's greater than 0, then this thing opens up. Or if A is less than 0, it opens down. Now, what's really cool here is that everything we just talked about here will apply to every function that we do from this point forward. So we'll do quadratic functions, we'll do exponential functions, well, those don't really have a vertex. We'll do cubic functions and quartic functions. We're going to do so many different functions, okay? And basically everything I just talked about here, about H and K being like your shifts, your horizontal translation and your vertical translation, about A, the absolute value of A telling you whether it's stretching vertically or shrinking vertically, about the sign of A telling you whether it opens up or opens down. That's all going to be transferred to every single function that we talk about. Okay, let's see. Anything else? I don't think so. I think we're good. Okay, so let's move on and do some problems. And notice everything that I talked about on the front, we also talked about in class while we did our exploration, right? So again, this function here, you should know that A is your vertical dilation factor. The sign of it tells you whether the thing opens up or down. H is your horizontal translation, and K is your vertical translation. Okay, and we talked about all that in class. All right, so let's actually do a couple problems now. We're just going to graph a couple functions here. So the first one I'll do, A, is going to be y equals negative absolute value of x minus 1 plus 1. Okay. So let's start with our h and our k. So remember, we're always thinking about this. Okay, that's basically every single function we're going to do is going to have this minus h plus k, and it's going to have some vertical translation factor. Or sorry, vertical dilation factor. Okay. So my h here, well, h equals 1, which means I've moved right 1 unit from where my parent graph is. My parent graph starts at the origin. So this graph is going to have moved 1 over to the right. All right, well, my k is also equal to 1. So that means I'm going to go up 1. And my a, if you notice here, my a, well, a is really, there's a 1 there, right? So the absolute value of a is 1. So that means it hasn't vertically stretched or shrunk at all. But what it has done is this right here, this negative, basically makes it open down. We call that a reflection in the x-axis. So this is reflected in the x-axis. In other words, it opens down. The reason for that Right, this one, A was positive 1, right? So it was opening up. Well, this one, all the outputs now are going to be multiplied by a negative 1, so that means that they're going to all open down. So that's a reflection in the x-axis. Imagine just folding this thing on the x-axis. It's now going to open down. Okay, so let's go ahead and let's graph this. So there's really no reason to make a giant input-output table. You should have a general understanding of what this graph looks like. I know it's going to open down, so I don't need too many positive y values because it's vertex. Or the HK, so our vertex is going to be at HK, which is 1, 1. Okay, so my vertex is going to be at 1, 1. Okay, that's also going to be that's my highest point because that's my vertex. I'm going to have an axis of symmetry in x equals h, or my axis of symmetry is going to be at x equals 1. And now what I can do, if I can find like 1 or 2 points to the right of this or to the left of this, I can just reflect it in this axis of symmetry. So I'll do a small input-output table. So how about I plug in 2? So I plug 2 in. 2 minus 1, well, that's 1. That's the absolute value of 1, which is just 1. Multiplied by a negative, so that's negative 1. Plus 1 is 0. Make sure you understand that. So when I plug in 2, I'm on the x-axis. And it's symmetric in this line of symmetry, so the same thing's going to be true on the other side. You get 3 points. I think you should be good. Having a y-intercept is probably pretty important. This thing's going to be a V going down on both sides. It's like 2 lines coming together. This one had a positive slope of 1, and this one had a negative slope of 1. Label your axis of symmetry. You should label our vertex too, even though I already wrote it up there. Okay, let's do the second one. So y equals 1/2 times absolute value of x plus 2 minus 3. And again, we're thinking about what's our A, our H, and our K. If we can find H and K, then we know what our vertex is or where it is. And then if we know what A is, then we're going to know whether this thing opens up or down. And then we can also think about if it's going to be skinnier or fatter than something than this, like this. Okay, so first of all, my A is 1/2. So because A equals 1/2, or the absolute value of A equals 1/2, this is going to be a vertical shrink. So my graph is going to look fatter than my parent graph. Also notice that right here, this is positive, right? There's no negative sign there. It's positive. So we know that it opens up. So the other part of this now, H and K. Now notice that in this formula I have x minus h. That's because truly h is, or I should say the x value is, if I have x minus h and I set that equal to 0 and I solve for x is h. Okay, so you have to remember it's always x minus h and then a positive k. All right, so here, well, this k then, because in the formula, remember, it's plus k. This k is negative. Okay, so this k equals -3. So that means we're going to go down 3. Well, what is this h? This h, if I were to actually solve for x, this is a -2. Okay, so, or you can think of it like this. This is really the absolute value of x minus a -2. So what is h? Oh, h is that -2 because it's x minus h. Okay, so here, h is equal to -2, so that means we're going to go left 2. Okay, so I got all my information. So at this point, this should be a pretty straightforward graph now. All right, so let's see what we're going to do here. This thing's opening up. I know that my vertex, let's see, I can go ahead and tell you that right now. My vertex is at -2, -3. And it's opening up. So I know I'm going to need to be in that third quadrant for my vertex. So I'll start with my vertex. That's also going to be where my axis of symmetry is, right? So I'm going to have this axis of symmetry that goes right through that vertex. So that axis of symmetry will be x equals -2. The vertex is at -2, -3. And now I can make an input-output table where I just plug in like one more point, and then it'll be symmetric with respect to this axis of symmetry. So I'll just reflect it. So let's see here. If I plugged in 0, then I'd end up with my y-intercept. So let's see what that looks like. So if I plug 0 in, I'm going to have 1/2 of 2 plus 2, or sorry, 1/2 of 2 of the absolute value of 0 plus 2 minus 3. So that's really 1/2 of the absolute value of 2 minus 3, or in other words, this is 1/2 of 2 minus 3. Doing a lot of steps here. So this becomes 1 minus 3, or in other words, -2. So I know that my y-intercept is -2. So when I go 2 spaces to the right from my axis of symmetry, I'm down to -2. So the same is true if I go 2 x values to the left. So at -4, my output will also be -2. So my graph is going to look something like this. Now notice, this is, I guess, call it fatter or shorter. I don't know, it's hard to kind of say shorter, right? And that's because, see the slope? Basically, when I go to the right, I have a slope of 1/2. And the same is true to the left, right? That's actually a -1/2, right? So it's a negative slope for this line. So in a way, this is like a piecewise function. Okay, so the key that you need to take away from this is this right here. You need to understand what A, H, and K do to these graphs. I don't want to see big, giant input-output tables anymore. Because if we do that, when we get to all, you guys are going to learn like so many functions this year. And if you don't understand the parent graph, right, like this is our parent graph. If you don't understand this, it's really going to hinder your ability to keep all these functions straight and graph